Welcome to CEDA-Labz. First, let's answer the questions asked in previous tutorial. First question was to detect which type of delay model is used in this circuit. So, delay model used is distributed model, as delay is distributed to each delay. Secondly, we have to design this circuit in Verilog. Here is the code in gate level modeling with delays. Next question was to design the same circuit via lumped delay model. In lumped delay model, largest delay is lumped on the output gate. So, the largest delay is 11 plus 4, 15. Here is the code. In this tutorial we will be studying lowest level of abstraction, switch level modeling and user-defined primitives. Earlier we learned digital design and simulation at a higher level of abstraction such as gates, data flow, and behavior. However, in rare cases designers will choose to design the leaf-level modules, using transistors. Verilog provides the ability to design at a MOS transistor level. Design at this level is becoming rare with the increasing complexity of circuits, and the availability of sophisticated CAD tools. Verilog HDL currently provides only digital design capability with logic values 0, 1, X, Z, and the drive strengths associated with them. There is no analog capability. Thus, in Verilog HDL, transistors are also known as switches that either conduct or are open. In this tutorial, we discuss the basic principles of switch level modeling. Switch level description implements switches or transistors to describe relatively small-scale digital systems. Switch level description is usually implemented in very large-scale integrated VLSI circuit layouts. It is the lowest HDL logic level that can be used to simulate digital systems. Only small-scale systems can be simulated using pure switch level description. If the system is not small, a huge number of switches are needed that may render the simulation impractical. In contrast to Verilog, basic VHDL does not have built-in statements such as NMOS, PMOS, and CMOS. That is why it is only possible in Verilog. And also it is not synthesized by synthesis tool. Verilog provides various constructs to model switch-level circuits. Digital circuits at the MOS transistor level are described using these elements: MOS switches, CMOS switches. There are two types of MOS switches, NMOS and PMOS. These switches can be defined with the keywords NMOS and PMOS. Keyword NMOS is used to model NMOS transistors and keyword PMOS is used to model PMOS transistors. This is how we can instantiate NMOS and PMOS switches in Verilog. Since switches are Verilog primitives, like logic gates, the name of the instance is optional. Therefore, it is acceptable to instantiate a switch without assigning an instance name. The symbols for NMOS and PMOS switches are shown here, and these are the truth tables respectively. The value of the out signal is determined from the values of the data and control signals. Some combinations of data and control signals cause the gates to output to either a 1, or 0, or to a Z value without a preference for either value. The symbol L stands for 0 or Z. H stands for 1 or Z. Thus, the NMOS switch conducts when its control signal is 1. If the control signal is 0, the output assumes a high impedance value. Similarly, a PMOS switch conducts if the control signal is 0. CMOS switches are declared with the keyword CMOS. A CMOS device can be modeled with an NMOS and a PMOS device. The symbol for a CMOS switch is shown here. A CMOS switch is instantiated as shown here. The N control and P control signals are normally complements of each other. When the N control signal is 1 and P control signal is 0, the switch conducts. If the N control signal is 0 and P control is 1, the output of the switch is high impedance value. The CMOS gate is essentially a combination of two gates, one NMOS and one PMOS. The power and ground sources are needed when transistor level circuits are designed. Power and ground sources are defined, with keywords supply 1 and supply 0 respectively. Sources of type supply 1 are equivalent to VDD in circuits and place a logical 1 on the net. Sources of the type supply 0 are equivalent to ground or VSS, and place a logical 0 on the net. Both supply 1 and supply 0 place logical 1 and 0 continuously on nets throughout the simulation. Though Verilog has NOR gate primitive, let us design our own NOR gate using CMOS switches. This is the switch level circuit diagram. Using the switch primitives we discussed, the Verilog description of the circuit is shown here. As usual, we will start with module name followed by port list. Then, output out, declared as output. And inputs A and B, declared as input. Internal connection, C, is declared as wire. As we already discussed, in transistor-level circuits, we need power and ground sources. Supply 1 represents VDD and supply 0 represents ground. So, PWR is declared as supply 1, and GND is declared as supply 0, and, then accordingly, PMOS and NMOS is instantiated. For this PMOS, output is C. Data as power and control is B. Similarly, for this PMOS, output is out. Data is C and control is our input, A. In similar manner, NMOS is instantiated. And, finally, module is terminated by AND module. We can now test NOR gate using this stimulus code. In similar manner, we will write the test bench, starting with module name, port declarations, module instantiation followed by initial begin block in which all the testing conditions are provided. And then, terminating it via end module. Here is the switch level Verilog code in circuit diagram for CMOS inverter. Here also we will start in the same manner and instantiate PMOS and NMOS accordingly. As we can see from the figure, for this PMOS, output is Y, data is PWR, and control is input A. Similarly, in case of NMOS, output is again Y, data is ground and control is A. At the end, module is terminated by AND module. And here is its test bench. Verilog provides a standard set of primitives, such as AND, NAND, OR, NOR, and NOT, as a part of the language. These are also commonly known as built-in primitives. However, designers occasionally like to use their own custom-built primitives when developing a design. Verilog provides the ability to define user-defined primitives. These primitives are self-contained and do not instantiate other modules or primitives. UDPs are instantiated exactly like gate-level primitives. But they are not synthesizable. If we instantiate UDP in any module, then that code or module will also be not synthesizable. There are two types of UDPs, combinational and sequential. Combinational UDPs are defined, where the output is solely determined by a logical combination of the inputs. Examples are basic gates, multiplexers, etc. Sequential UDPs take the value of the current inputs and the current output to determine the value of the next output. The value of the output is also the internal states of the UDP. Examples of sequential UDPs are latches and flip-flops. These are the distinct parts of a basic UDP definition. A UDP definition starts with the keyword primitive. The primitive name, output terminal, and input terminals are specified. Terminals are declared as output or input in the terminal declarations section. For a sequential UDP, the output terminal is declared as a reg. For sequential UDPs, there is an optional initial statement that initializes the output terminal of the UDP. The UDP state table is most important part of the UDP. It begins with the keyword table and ends with the keyword end table. The table defines how the output will be computed from the inputs and current state. The table is modeled as a lookup table, and the table entries resemble entries in the logic truth table. Primitive definition is completed with the keyword end primitive. UDP definitions follow certain rules. UDPs can take only scalar input terminals, that is, 1 bit. Multiple input terminals are permitted. UDPs can have only one scalar output terminal, that is, 1 bit. The output terminal must always appear first in the terminal list. Multiple output terminals are not allowed. In the declaration section, the output terminal is declared with the keyword output. Since sequential UDPs store state, the output terminal must also be declared as a register. The inputs are declared with the keyword input. The state in a sequential UDP can be initialized with an initial statement. This statement is optional. A 1-bit value is assigned to the output, which is declared as register. The state table entries can contain values 0, 1, or X. UDPs do not handle Z values. Z values passed to a UDP are treated as X values. UDPs are defined at the same level as modules. UDPs cannot be defined inside modules. They can be instantiated only inside modules. UDPs are instantiated exactly like gate primitives. UDPs do not support in-out ports. Both combinational and sequential UDPs must follow the above rules. Each entry in the state table has this syntax. In order to understand how state table entries are specified, note the following points about state table entries. The input values in the state table entry must appear in the same order as they appear in the input terminal list. It is important to keep this in mind while designing UDPs, because designers frequently make mistakes in the input order and get incorrect results. Inputs and outputs are separated by a colon. A state table entry ends with a semicolon. All possible combinations of inputs, where the output produces a known value, must be explicitly specified. Otherwise, if a certain combination occurs and the corresponding entry is not in the table, the output is X. Use of default X output is frequently used in commercial models. Combinational UDPs take the inputs and produce the output value by looking up the corresponding entry in the state table. If you have read rules thoroughly, you will be able to write UDPs very easily. It is very simple. We start with primitive keyword followed by primitive name and port list. Then, ports are declared in declaration section. Then comes the state table entry, which is same as the logic table. We can change the values of output accordingly, as it is user defined. Table is ended by the keyword end table and primitive is then ended by end primitive keyword. Similarly, here we design user-defined OR. Compare the parts of these UDPs with the parts which were discussed in module definition. The missing parts are that the output is not declared as register and the initial statement is absent. These missing parts are used only for sequential UDPs, which are discussed later. We will start with the keyword primitive name followed by port list. Then, out being declared as output and A and B being declared as input. With keyword table, we will start the state table entry. We will mention all input conditions and respective output for them within this state table block. And end this table with the keyword end table. And primitive is terminated by end primitive. Notice that this example covers all possible combinations of A and B, where the output is not X. The value Z is not allowed in a UDP. The Z values on inputs are treated as X values. In the last example, whenever one input is 1, the result of the OR operation is 1, regardless of the value of the other input. The question mark symbol is used for a don't care condition. A question mark symbol is automatically expanded to 0, 1, or X. The OR gate described in the last slide can be rewritten with the question mark symbol. Question mark represents don't care condition, that is, whatever may be the condition. So in state table block, second condition represents whatever may be the first input. If second input is 1, output will be 1. Similarly, third combination represents if first input is 1 and whatever may be the second input, output will be 1. So, as we can, all the input combinations are covered within these two combinations, unlike we did in the last slide. This is the significance of don't care condition. Sequential UDPs differ from combinational UDPs in their definition and behavior. Sequential UDPs have the following differences. The output of a sequential UDP is always declared as a register. An initial statement can be used to initialize output of sequential UDPs. The format of state table is slightly different. There are 3 sections in the state table entry: inputs, current state, and next state. The 3 sections are separated by a colon symbol. The input specifications of state table entries can be in terms of input levels or edge transitions. The current state is the current value of the output register. The next state is computed based on inputs in the current state. The next state becomes the new value of the output register. All possible combinations of inputs must be specified to avoid unknown output values. Also, if a sequential UDP is sensitive to input levels, it is called a level-sensitive sequential UDP. If a sequential UDP is sensitive to edge transitions on input, it is called an edge-sensitive sequential UDP. Level-sensitive UDPs change state based on input levels. Latches are the most common example of level-sensitive UDPs. As it is sequential UDP, output needs to be declared as register. In level-sensitive latch, if clock is 0, Q retains its value, whatever may be input. When clock is 1 and D is 0, whatever may be the value of current state Q, next state Q plus will become 0. And when clock and D both are 1, whatever may be the value of current state, next state will be 1. Edge-sensitive sequential UDPs change state based on edge transitions and or input levels. Edge-triggered flip-flops are the most common example of edge-sensitive sequential UDPs. This is how we represent clock transition. When writing 0, 1, it is positive edge transition of clock, and when writing 1, 0, it is negative edge transition of clock. So, on the positive edge of clock that is transition from 0 to 1, Q gets the value of D. If clock transitions to negative edge of clock, it do not change the value of Q. Also, if D changes when clock is steady, holds the value of Q. Now, let's move into the flashback. In this tutorial we learned switch level modeling, types of switches, and then we did some examples in switch level modeling. Further, we studied UDPs, rules for writing UDPs, its components and its kind, combinational and sequential UDPs and their example. Some questions for you. I hope you'll be able to answer them.